So thank you all for coming. Today we have Carlos Peña Garay from, I can't say it in France, but the Subterranean, Spanish, the Subterranean Institute, essentially, the underground lab. And he's gonna talk to us today about science in the underground lab. Carlos did his PhD at Valencia University before he actually came and did a postdoc at Princeton, so just down the road. He was telling us earlier he was originally a chemist before he moved into theoretical physics, and now he is the managing director of the Subterranean Laboratory Canfranc. Yeah, so please, whenever you're ready.
Okay. So yeah, maybe there are not many theories just in underground labs. But in fact, the pioneer of the underground lab in Canfranc was a theorist from University of Zaragoza in the 80s. There's a famous story about him. Ángel Morales, he's one of the fathers of this talk meeting series and many other things in the 80s. But he was a theorist in the department of University of Zaragoza, so he drew a line and he moved to the other side, and most of the department was theorists. And he said, the ones that want to come to me, we will start working in underground science. The others, you have to look for yourself. And that was how the underground lab started. They started just using an abandoned tunnel, and then afterwards, things got improved. And in the meantime, there was other bigger labs going on. But what I want to tell you is which is the type of science I'm interested in, and which are the type of things that I do to hopefully contribute a little bit to improve in the direction of how we want to understand and what we want to understand about neutrinos. But being in underground lab, you have to face a variety of things, and then also the ones that build experiments know very well that you have to be patient, that things take time, etc. And then for theories, this is a little bit tougher. So we really are more kind of trying to have some creativity. So this I did my best in the last 5 years in Canfranc. So I will try to explain about that. Let's start by something simple that you know, but something at least that you know, which is the standard model. This is the standard model in one option that might be, it's very non-appealing and it has some problems. That this is, well, let's try neutrinos like if they were the other Fermion spinors. In that case, we have just to have neutrino masses. We know that neutrinos have masses, and then some of us, about 20 years, were participating in concluding with experiments and theoretical interpretation that neutrinos, that's the only way. These two of them, we know today that they have masses, and probably also the third one, that very likely. But the standard model then imposing gauge symmetries SU3 cross U2 cross SU2 cross U1, and the family content, the Fermion content, is chiral fermions. Then you can build all terms allowed by symmetries. And in those terms, if there are no right-handed neutrinos, everything is fine. You put everything that you can. One exception. But if you put right-handed neutrinos, then you can do it. Then it will happen like with the other fermions. You will have to build, well, the term for the kinetic energy, then you have a coupling through the Higgs. I didn't apply spontaneous symmetry breaking so far, and this is how you build, and then you have equivalent to the CKM. There are people here that are also working in the quark sector. Then here we have also equivalently one matrix that depending, well, you reabsorb phases, and then you have three angles on one phase. But there is an issue, and the issue is that if you have right-handed neutrinos, then you have masses for neutrinos, you have masses for the other fermions, and then you could just ask yourself why the masses. Remember, this is for families, 1 family, 2 family, 3 family. This is a graph made by Toshi Murayama many years ago and represents to me quite well why we are so surprised that neutrinos are here. Those are the 3 families. But those are masses. Here, masses in favor are equivalent. If you have studied oscillations, you may know well why in the quark sector we don't see directly this, and then this is because of the coherence. But In any case, we see that there are 1, 2, 3, 4, 5, 6 orders of magnitude or more to the rest of the content. And within a family, then the separations are 1 order of magnitude. You can take it like that. So those are parameters. We live with those parameters. We are happy, and that's all. But we could have stopped science centuries ago if that were the attitude. To me, this is a big surprise. To most of us, then that work on this is an extraordinary surprise. This cannot be for no reason. It's too many orders of magnitude. The other thing that is another fact that tells you that something is different in the lepton sector is that, as you know, as quantum states, the fields, they don't have to be the same, the flavor states and the mass states. And then this relation among them is this unitary matrix with mixing angles. And here is also a word to represent is the content of the mass states in flavor states. So it's the state that is in lowest in mass have more content of flavor mu e, a little bit of mu and the same mu tau, and the same for the others. And those are the two ways of reorganize the possibilities of masses. So if you have a look on how this is for the core sector, you will have basically here blackish, with very little color. Here is bluish, with very little of the others. And here reddish, and very little of the other. And then you can ask yourself, this is just by chance? Maybe, as I said, you can take numbers and be happy with that. There is no theory yet established for these observations. So you can say, blame on us, blame on theories, and say something. But there is something that is mandatory. Is if you take this first option, saying, well, forget about that, neutrinos are Dirac and don't believe on these people, you have to explicitly, or you are implicitly imposing a symmetry to prevent that this term doesn't appear. So I mean, you are saying SU3 cross SU2 cross U1 potential symmetry plus, of course, one particular symmetry. It's okay. So you can say, well, now I don't like the hand in the two ways. So I make that this side and this side in the hand are the same, and we live with this. So I think there's a consensus that this scenario doesn't look at this a way to make progress. And then there's an alternative already identified by Ettore Majorana in 1937, finding an alternative solution to Dirac spinors, in that case for neutral fermions. So if told in a different way is if you add these right-handed terms, and then you add that term, you can have constant with units of energy multiplying the fermions, and this is the way to write it. But forget, at the end you will have a term with null, so it means the standard component of the doublet that has weak interactions. Then you will have the cross ones that are the ones that you observe thanks to the Higgs, or you have thanks to the Higgs, and then you will have this term, right-handed times the mass, and this is this term. And because the right-handed, they don't have any charge, you can add to the Lagrangian. And this is how I see it. So that means, to me, the interesting thing about the standard model is not making it a group bigger and bigger and bigger. We can do that. And in fact, it's a very interesting mathematical exercise. And even going to not fields, but these things. But to me, it's even simpler looking at what is left in the standard model. Okay. There are these two terms. One is this mass. The other, and I will talk a little bit, is some G bar. So this is that violation of parity term that should be in the Lagrangian, and because of measurements, it has to be somewhat cancelled miraculously. So the standard model, if you just take gauge symmetries and you ask yourself what should be there should be these two terms. So let me just now discuss which are the type of areas to me of interest, just try to explore whether this is true or not. Okay, the most popular, the most hardly easy to apply or to try to discover is try to find this very rare decay, if it exists, which is going from a 0+ to a 0+ state, is a decay where 2 electrons, so that means the nucleus changes from 2 protons to 2 neutrons, vice versa, then you produce 2 electrons. And in that case, if neutrinos are Majorana, they can cancel each other, and there is another diagram that produces only 2 electrons, and this is neutrinos that are decay. And certainly some of you should have been facing this process. There are 3 terms that contribute to this observable, calculated. One is very well known, and then you have a professor here. Is he around?
He's emeritus.
Oh. Okay, so he has this renowned paper where he did this precise calculation, and it has not been improved anymore because he did it perfect, but that's okay. And everybody knows and takes the number, takes the factor, and it's fantastic. And it's quite precise because at the end, this is the phase space that you have for the process. There is this ugly part, and I took it, this is from a very recent paper, and also population from someone from here that was presented in TAB a couple of weeks ago, which is what is the dynamics that makes this process. And about 20 years ago, with John Bacall and with Hitoshi Moriyama, we wrote a paper complaining how large was this spread. This is spread in calculations done for about 30 years with different methods. And the nuclear community, of course, were very unhappy with our statements. But at the end, it helped the community to realize that something has to be done here. It cannot be that we give Karsten and others tens of millions of euros, and then we cannot tell anything about where the signal should be. At least we should at least put a few millions of trying to improve that. And in fact, congratulations. This, for the first time in many years, has been done here in the US, and there has been a significant effort to try to improve all these calculations. Most of the problems with these calculations, they were known not only in nuclear physics, but also in chemistry, which they do many more calculations than us because they get more money for the benefit of these calculations. In this case, it's with electrons. And one of the things that if you use phenomenology to help your calculations, many times you double count processes. So it's very difficult to understand whether you are higher or lower with respect to your value, and that's why you have these largest spreads. So this spread, by the way, here you can see now that things improve in 20 years. We found out that it's about factor 2 to 3, that the squares is almost 1 order of magnitude. And lack of knowledge of where it is, how life it is there. 1 order of magnitude for Karsten and others, maybe is 20 years of work. And 1 order of magnitude, the larger cost for the detector. So I think improving this is a very important task. And for the ones that have been following may know it, there has been good things happening. And the good things happening is that, for example, an old problem of understanding beta decay has been recalculated with ab initio methods where you don't use phenomenological parameters. And then this problem has been fixed and understood. That was, of course, part of the not the ab initio calculation. And now they are just working very hard on doing the same for business units that are beta decay. The bad news is that probably the values are a little bit down. Going down here, this is inverse of half-life, means half-life is longer. So it will cost a little bit more to observe this signal. We need to know what it is. It is true that depending on which is the largest uncertainty is in how you go from the basic interaction, from the quark interaction to the interaction at the level of nucleus. But this thing will continue improving. So I got interested in this problem, not only criticizing it, but thinking about it. So I will discuss just very shortly which kind of things are we doing. This is the second issue, which is here, because in this process that you have this change to neutrons, 2 protons, 2 electrons, and the neutrinos don't get out. And then you have this mass insertion, which is being changed. And then you have the sum of the neutrino masses. So here is a sum of M1, M2, M3, weighted by the fraction that these masses, these states are electrons and phases. So this is a simple formula that you can just go and calculate. And before I was saying, it's very good that you do it by yourself, because whenever you see these plots so common, etc., are so confusing. So in here, I'm representing probably in a different way for some of you. This is this element matrix. Remember, this comes square, this element, as a function of one of the masses. The other two masses are quite precisely known, because then we have the splittings measured by oscillations. And then this is one of the two phases. There are two phases in this formula. And then this is interesting. So this element comes from almost a little bit lower than 10 to minus 1 now, given the well we know the lightest mass should be smaller than 0.1 electron volt or so. So, and then you see, and then we have two slices, the two ways of ordering masses. But the relevant thing here, I'm representing here the minimum, by the way. There should be another one on top of it. This is for normal, for inverted, this is for normal. And the one thing one can see here is that depending on the particular values of parameters M1 and ρ, then you see that there are some kind of cancellation. So MEV could be very, very low. This is true. But this will be extremely fine-tuned. So you see, you have to be in this kind of thin slice. This part is empty. So, and this is something that happens in theory all the time. So you have parameters, and then you have to explore the parameter space. And most often you cannot explore 100% parameter space. It will be a great experiment if you can cover all possibilities. Most often you don't do that, but the important thing is that when do you cover 90% of the parameter space? And then you don't have to go so low. So it means this number, 10 to minus 3, I mean, milli-electron volt, is the target. Of course, before getting to 10 to minus 3, I think others will say, well, let's fix 10 to minus 2, and then we'll go to the next one. But at least there is a limit. And this is the minimal scheme that produces that effect. So that means that phenomenon. Any other way that we produce neutrinos double beta decay will be more exotic and will have new particles and new variations of the standard model. So I think this is a kind of, I think it's agreed widely that this is something we are going to do as humans. It will take it our generation or your generation, but this will happen. We will just explore until we go to something here. And if we don't discover this, it is to say, oh, maybe there is a fantastic symmetry, very curious. No, it cannot happen. So maybe nature has something even hidden to us. So let me just say 2 or 3 things that I'm interested with respect to these programs that have to do with science, and then I will go to the underground lab. The very first thing is that, can we do something more than doing theoretical calculations that improve with improved methods? The answer is yes. And this is what we try. This is with in the lab. We have also PhD students. This is with Beatriz Romeo, and this is a work that she did also with someone world expert, that this is Javier Menendez. And this is, you can do calculations of the double beta decay process, the matrix element, and for the same nuclei and the same nuclear interaction, then you can do for other processes that share a spin and isospin structure. So therefore, that there should be some connection, at least at the nuclear structure of the different gamma matrices, etc., etc. And then this is what we observe. We observe that there is a correlation for different nuclei. These represent different nuclei, where you can just see that there will be some spread because even in these methods, these are not these ab initio methods. Then there are different nuclear interactions assumed for doing the shell models or for the other. In this case, it's shell model. You can see there is some spread, but there is a correlation. So that means if I know one of the elements, I could predict the other. This is how theory is encoding the lack of uncertainty. So instead of having something uncertainty in this direction, then at least I can reduce in this way. So once we did that, this is with a process, by the way, that has not been measured. It's a beautiful process. It's in this case a 2 gamma decay. Not from the, if it is 2 gamma, then you don't have 2 neutrons to 2 protons. So it's 2 gamma from the double isobaric anaerobic state. It's doable, but it's an experiment in itself. Hopefully much simpler than neutrinos double beta decay. So this would be one way. Then immediately when we did this calculation, so to the team, some referees said, why don't you do the same with double beta decay with neutrinos? Should it be correlated, etc.? And with some characterization, again, you have this correlation, but double beta decay has been measured, so you can try to infer from the double beta experimental number what would be the neutrino double beta decay matrix element. And still, with the current uncertainties, etc., you cannot beat the theoretical, but this is not as theoretically dependent on the other. This is something that with ab initio calculations will improve significantly, and is one way to go. At least just to reduce some of the contributions to the matrix elements, change normalization. Again, in these correlations, when you just remove this, the lack of knowledge that you have in the normalization. This is one other way. Let me go to the second one. It's taking along to determine the structure of the masses of the neutrinos. So these neutrino oscillations were determining that we have at least one splitting and other splitting in 2002, and well, a little earlier, but very well defined 2002 and 2003. Since then, well, we still are there. We cannot determine whether there are one splitting is higher respect to other, or the other splitting is lower respect to the higher. So this structure that I call in our business normal animated, so which is the type of structure in masses. This is much larger than this by a factor of 30. So some people like me advocate that it will be very difficult that nature has chosen inverted hierarchy. And the reason is the following. Some of us, if have to bet, or if I have to understand how the standard model and the new field that creates masses beyond the Higgs does for neutrinos, will tend to think that it will be the same mechanism for the 3 neutrino masses. It will be, it's possible, but will be really hard to understand from the construction that we have been doing in the standard model, that each neutrino takes masses from a mechanism completely different. That means that whatever mass gets one neutrino and the other, they cannot be crazily different. That's one assumption. Second assumption is that there is no symmetry that says you have to be in this point of this parameter space. It may happen, you always live with that, but this is what always limits using Bayes inference. I think you said that you work in lots of things, statistics. I don't know if in your field also now more and more Bayesian inference is used, but this I think came to help in some problems. And also, well, we are going to use some cosmology limit, and for particle physicists, talking about cosmology sometimes is like, this is a fantastic science with lots of data and with a simple model, like the standard model, and maybe compromised by other components, but it's very difficult to fake those observables in so different scales. So if this is not compromised on these three assumptions, my claim is that there is very little chance for inverted hierarchy. And the reason is that at the end is when we say what is the lightest mass, what are the structure of possibilities for one mass and the other, this has been expanded by a factor of 10 just to be visualizing. This is very thin. This is very thin because this is the one to the splitting. So yellow determines the possibilities, the choices that are for the mass 2. Remember, there are 3 masses. Here there are the number of possibilities. The number of possibilities keeps growing in a logarithmic scale. So if you make this ratio, this is telling you that the nature has to choose, then has more space here than there. And this is the argument that you do when you do a Bayesian analysis. So the more that this cosmology limited goes down, then the more is stressing that there is no chance for inverted hierarchy. This is changing a lot our picture. Remember, for Karsten and others, they will have to keep 10 to the minus 2 to 10 to the minus 3. It's not that they like it 10 to minus 2 if you want to ask for many millions, because you say that you have a target. But I think normal hierarchy also has a big space in the knowledge. Okay, that was my comment respect to the second point. And then the third one, which to me came as a surprise, that the calculation was in such a way of observing the effect. So distinguishing Majorana from Dirac only happens because of this Majorana master. So it happens when you have observables sensitive to the mass. If neutrinos are relativistic, that is what happens most often, no effect. That's why in neutrino oscillations, you don't see difference between Majorana and Dirac neutrinos. But if you go to when neutrinos go lower in energy compared to their mass, then you start seeing non-relativistic effects, then you can see differences between the master. And this was observed by long lunar linears and Szilard, and then they did this calculation, but they assumed that neutrinos are completely non-relativist. So, and they notice if those neutrinos that are very hard to detect because they are very low in energy, but if they were detectable, the rate is very different from Majorana or Dirac. We did this calculation in detail, taking into account that some of the neutrinos are relative, but more relativistic, nonetheless. But the main idea why the calculation has some influence is the following. So in particle physics, we all know about helicity. And relativistic particles keep helicity. In the case of neutrinos, they are left-hand, right? The neutrinos, they are left-hand. So if nothing happens, if there is no, whatever interaction we have, because it's chiral, they will maintain left-hand neutrinos. But gravity may change direction of neutrinos without affecting the spin. So helicity may change by gravity. And this is what we calculated. We calculated how much the direction of neutrinos changes when it crosses an halo. And it changes quite a lot. And this is how the angle respect to the original direction of the neutrino changes when it's traveling from redshift 3 to us, to now. And then it was, of course, it's going to depend on the mass. The larger the mass, the less relativistic, the more it changes, and therefore the more changes the rate. And here are the numbers. So if in one day there is one experiment with 100 grams of tritium and sufficiently good energy resolution to just take those neutrinos apart from the beta spectrum, then you will see, they will count at some number. This is the numbers that you see for different scenarios. So this is 809 is what you will expect in Majorana, and half would be if they are there. And those have these different scenarios depending on how light is the lightest. So it's not only neutrinos that are beta decay that will demonstrate it, but also at least this will help or tell us that we are on the right track. So let's come now back to experiments. Why a theorist goes to this hole. There are many underground labs, and this is, I think I was told, the first used for particle physics, radioactivity, etc. It was used by Wilson, and the story is very interesting if you don't know it, because he tried to demonstrate one question at that time, at the beginning of the 20th century, is whether radiation was coming from the Earth or was coming from above. And most probably you know who was the one that won the Nobel Prize because of that, going in a balloon and learning that the radiation was coming from above. But this was a good idea from him. He said, well, if I go inside the Earth, I'm getting protected from something that comes from above, and if it is above, it should go down, right? And if it is from below, it should go up. And it went up. And the reason is that this was 100 years ago, well, 120 years ago. Radioactivity was not understood at the level we understand it now. There was lots of rhythm, and therefore the signal, and this happens in many of our experiments sometimes when we don't understand, is we get more than we expected, but we were right. The idea was good, but we didn't understand many of the things that were contributed. So in that sense, the conclusion was it didn't help, but it was the first use of an underground lab. This is in Scotland, by the way, in NPA. Since then, there are many underground labs. Many. Well, we could, some of them are underground labs, some of them you could call it facilities, etc. And these are nice plots made by Jared from his lab. And then in here is also shown size represents the volume. So that means the bigger places now, I thought it was Gran Sasso, but it seems that Sort is becoming now the largest. And Hyper K, when the hole is finished, would be the largest, but would be one experiment, not a facility. So, and there are lots of them with different sizes and in different parts of the world, not many in the southern hemisphere. So lots of activity. And the other thing I like about this is that you see how these colors are changing. This is what is expected. So it means this is how volume is going to grow. And some of them are some new labs that are going to grow. It's an area where it seems that we will have more activity in the coming decades. Something that maybe is new for your director here. So some of the labs in Europe, so Europe is very peculiar. For the Americans, maybe sometimes is. So we have many labs. Because of course we have our history, and then we are countries with different stories, etc., etc. But now most of us, we don't have our UK friend. Most of us are European Union, and there is some kind of idea of trying to make a better use of them. And then that is very difficult because we get money for each country. So that means this is not a European money. But we started. And this is an agreement that already we got the document, and it's just in the last phase of signature, etc., between Canfranc and Gran Sasso. And this is for the ones that are Quarry or Cupid. Then it's an advantage because that agreement says that if you are LNGS staff, I think you are not LNGS staff, but if you are LNGS associated personnel, you are, because you are experimental collaborations or approved research activities, you can access Canfranc through a mechanism that we will have to the safety officer and following some rules, etc. You can use also the services and spaces and also collaborate with similar groups, etc. through a well-defined protocol. This is created because, as you know, as scientists, we love just to go to a friend and say, what do you do here and there? It's just to make easy. You don't need friends. It's okay to have friends, but you have a protocol just to do this. Will make more efficient your work in the other. So it's I think this is pioneered, this certainly in Europe. I don't know if this happens in other places in the world, but we think that this will set the standards to do with the others. For the ones that have not been in Canfranc, if you divide the Pyrenees, the separation between France and Spain 3, we are in this first 3. This is the Basque Country, etc. So we are over here in the region that is called Aragon. We have 800 in vertical of overburden. The lab, as I said, started using a tunnel, a train tunnel. By the way, the place is spectacular. It was an international train station, French style, very beautiful. Now it's renewed as a 5-star hotel deluxe, so quite expensive. Maybe not for the US standard. In any case, it's operative since 2010. 260 scientists from with several experiments from 50 institutions. Those are some numbers and parameters that say where we are. And this is a picture from the back of the main hall. So compared to Gran Sasso, it's about 1/6 in some numbers. But just very quickly, just to show some of the activities that may be relevant to this community. About an X experiment, that I think there's also a strong connection with the activities here. With the current data, they have this annual modulation excluded at 3 sigma. They started this August, the last 7th year of data taking and will not continue anymore. They are reaching now the wall. And they hope to reach 5 sigma exclusion. See? You know, this was a must. And I remember that town meeting in Seattle 20 years ago. And at that time, it was John Paul making a claim. Because after 10 or 15 years, there was Dama Libra claiming that there is dark matter and nobody was doing anything. And luckily, some activities, I think it was by you and other colleagues, right? Then the people in Spain and also Italians with Saber and Princeton. Luckily, well, we will close that chapter at some point. So then there is another experiment using about 1 ton of liquid argon that is going to be used as a veto for having another cryostat inside to measure the activation of the underground argon extracted from this Colorado place for dark side, maybe also for agent, etc. So having argon as a scintillating active veto, but not radioactive. Then our kind of flagship experiment is NEXT. This is a picture of NEXT that had inside a few kilograms, and I will mention in everything soon what is the status of the next phase. They finished in 2021, and this was a technology to see the tracks of the electrons. And then if you see the tracks of the electrons, you see 2 tracks respect to 1, because they have 2 blocks at the end, and it's very easy to distinguish. In fact, this worked very well, because then have a 27 factor extra of radiation of background using half of the efficiency, more or less. And also energy resolution is pretty good. It's not crystals, but it's not liquid, so it's in between. So this here is 0.9. We will have maximum, and in crystals probably is about 0.1, 0.2. Which, okay, makes a possibility. And with only 3 kilograms, they have this half-life. But the current situation is 10 to the 26, and Cameron's probably will improve it at 10 to the 27 in a few years. And then we have something very much connected with this, with one of the areas here that is related to Cupid. There is a Cron's demonstrator, a dilution fridge that can host a number of crystals, not a small number. And that the motivation was studying, I think with scintillator, one of the fantastic things of Cupid is that it will be very easy, but very efficient remove alphas. The question with betas from surface is going to be the challenge, and some of the research has been in that direction. And if I understand correctly, this demonstrator will help a little bit Cupid when you do works on crystals. So that means you will bring your crystals to Canfranc. So I'm happy to come here to tell you your crystals will be welcome. Just to finish with some more things, so I will talk about this new germanium detector that is very important for some experiments characterizing ultra-pure materials, also ICP-MS. We have a strong activity in hyperkamiokande. Hyperkamiokande is the other beast that is also facing Dune. Dune and Hyper-K try to go to ultra-large detectors, and we have to do fantastic things like going to Palma de Mallorca in the Mediterranean in a nice boat. There are no rings, but at least you can have nice weather over there. And then we go and make some immersion of these PNTs inside PNT covers, 80 meters. And we have to demonstrate that if one of the PNTs implodes, you prevent the chain reaction. This is something that for the youngest may not know, but that happened in Super Kamiokande about 20 years ago. And it was about 6,000 PNTs or so were broken in a few milliseconds. So this we developed the engineering of these, also the covers, etc., and also the test that you have to do by yourself. So it was lots of fun. I was on the boat. So next 100 is now completing and this is an image a couple of months ago on all the TPC internal. Even you can see here the electroluminescence amplification area. The bottom part is where the SIPs will go, and then this will be covers xenon inside. they should start in November 30, the 100 kilograms phase for this. Let me advertise things that we have been working on, and this is the goal with Wright in Canfranc. I mean, if we try something, at least let's try to improve for the benefit of community, because will be needed. In experiments like NEXT, you need lots of copper. For next 100, we got 15 tons of copper. Even that part of it gets removed, it's so much copper that unless copper is extremely clean, you will be introducing lots of radioactivity there. So it's not only just having it clean, also measuring it. So you need better and better sensors, and one of them is these ultra-pure germanium detectors. In the same way that was a shame 20 years ago not having replicated Gamma Libra independently, to me it's also a shame that there has been this detector, a germanium detector, made by Max Planck Institute, Heidelberg, more than 20 years ago, and has been the best for 20 years. And since then, they have been in the world about another 50 germanium detectors for screening. Well, we need this kind of germanium detectors, and with work, of course, it's not easy. It takes years for us, including pandemic was about 5 years. But now we have the first in place, which improves, and it still is works, and it still is a little radioactive, so this will go down. Some lines will go down, and then they continue. So this will be fractionally better than this. It will become the world record. And we are building the second one, trying to improve, and preparing for next year the third one. So we will have a station with 3, upper class high purity germanium detectors. So it's not just for fun; it's just for use by the community. What we do, what we do, hypergamma, I don't know, there's, I know, but there is no big contribution in the US for hypergamma. So I will just make a very quick update. Probably some of you now know also from many conferences. So one of the main issues is making such a big hole goes on schedule. Following Japanese standards, in fact, it's two weeks ahead of schedule, which is very standard to say that everything goes well. For all the others, of course, we are stressed because we have to build many components. There are many European countries contributing, Italy, UK. Also, of course, our countries are contributing to Dune by different groups. So this is going well, and one of the key issues is that everything has to be ready in summer 26 to be installed and start operation in 27, which is basically tomorrow. The physics program is wide and very interesting. There will be some significant improvement in proton decay half-life, not in coupling, but that goes squared fourth power. There will be also much bigger atmospheric supernova neutrinos, rally neutrinos, more size or more. And then an example, for example, one example just to comment is with respect to supernova neutrinos. It will be sensitive to a supernova in the closest galaxy. And then, but they got the money, or we got the money, because we have to demonstrate whether there is CP violation in the neutrino sector. And again, this is parameter space. And what it says this plot is that depending on the number of years, which part of the parameter space of delta, which is at the end 0 to 90 degrees, you will show that is different from 0, different from CP conservation, at 5 sigma or 3 sigma. So this will cover 60 or 80% of the parameter space. That's the best we can do with such a big risk. And I showed these pictures now. You can see that we were on the boat and then doing this kind of activities. We have several responsibilities, but I will not go into the details. But yes, building these covers is a lot of engineering that you have to fix many problems. And now let me just finish with some other thing that has to do more with this other piece that lacks in the standard model. And it's one of the problems I've been thinking about it since my Princeton times, more than 20 years. And for a decade, I didn't write any on this because most of my ideas were just nuts or failing. So maybe if you insist, at the end, some good idea comes. The very first thing is that there is lots of desperation. I shouldn't say that word. There is lots of lack of patience. Many people get desperate and then just propose very exotic solution. This is a very natural scenario that we should test. There is a term that is not in the Lagrangian, and we would like to understand whether this is true or not, why it's not there. This is the prediction that you will have for that term to fix why QCD does not produce an electrodipole moment in the neutron. And as you see, you have lots of freedom in the parameters that you add when you create a model that has an axion. Then you have lots of possibilities because you can have only one extra heavy quark. Exotic is not a standard model quark. Or you can have different values of the anomaly coefficients for electromagnetic and color. Depending on that, then your prediction may vary. I said at the beginning, that's the thing. Theoretically, this is a beautiful idea. From the point of view of prediction, you see there's a spread on possibilities. But at least we know where it's hard to see anything. So life is going to be hard because the discrepancies are small. And the other thing is that these actions have to be produced, and if we want to detect and they are dark matter, there is a possibility that these actions, that in principle is an issue with a standard model of interactions, then it happens that they may be dark matter. And depending when they are produced, then they have a mass or not when after the QCD phase transition, and then you have one mass or the other. And then this is the typical range that is reasonable within QCD. That means one thing is QCD, and the other thing is these functions are dark matter. They might not be dark matter, but it is very plausible that this scenario that will make me understand or make us understand why the standard model doesn't have one particular term will be in one of these places. This area has been widely explored by pioneer experiments here in the US. ADMX is kind of the landmark. But one of the things I look is life here is very difficult because the frequencies are higher, and then amplification is going to be amplification at low temperature. There is no technology. So, because I'm a theorist, then I thought, can we do something with this? Before that, I noticed that there are other possibilities, and one is spontaneous emission that is stimulated by the photons that are in space in the cosmos. But I let it there. Let me tell you what we are doing. So the experiment is called CADEX, for Canfranc Action Detection Experiment. I helped to promote it. Luckily, I don't have to do much. This is lots of engineering on telecommunications and electromagnetism, etc. But the good idea that we have is that it's a multi-cavity system. Multi-cavity is a cavity, you have a resonant cavity. So you have the size, the right distances, so that means that the wave is resonantly enhanced, which are the Q value of the cavity. But then you have a small volume, so there are very little possibilities for actions just to become an photon in a magnetic field. I don't know, I went too fast, but the main mechanism is that if you put a cavity where actions are floating around in a magnetic field, what you will find is from nowhere, so it's from nothing, then you will get the radio frequency. Very weak. So what we did is design how this has to be designed so that the electric field points always in the same direction. This was an exercise that telecommunication people will never think about it. Why? I don't care about the electric field. The only thing is this as a filter only allows some frequencies to pass. So you know, there is some freedom. You can design in such a way that always electric field points in the same direction. This is much needed because then the conversion will be additive. So I mean the volumes add. So we did that. We did that first for 8 gigahertz. Now we are doing for 90 gigahertz. We need to tunable. So I'm very interested in people here know how to move things, small things with lasers, because tuning some cavities that are millimeter or 2 millimeters is a very problematic thing, and technologically it's a challenge. But then this is going to create 90 gigahertz is radio frequency going almost to optics. So it means you just take this, you get out from your antenna. This is in a magnetic field, low temperature to have little noise or minimize noise. And then you go to some sensor, and that's the issue. So a 90 gigahertz, cosmologists know that very well. They amplify and they use kits in that. So superconducting systems. The technology is moving from being wideband to narrow band. And this is what they are developing some part of the scientists in Spain with some people here in the US. So at the end is a dilution refrigerator, like the one, or fridge, like the one that you use for other applications. But has a complication, you have to add a magnet. Has another complication, you have to add an optical system. Another complication has to be at millikelvin in a place where there is no magnet. But once you do that, you have a fantastic search of actions in this region. If you ask theories where the mass of the reactions will be, they will tell you, we don't know, but the tendency with better calculations is moving towards this region. So even that this is the best explored, today we know that most probably it should be here if there are actions. And now let me just finalize in the last 2 minutes with some of my entertainments being in underground lab. As I said, we have time to think, and one of the problems that physicists face is constantly that muons are ionizing the medium, creating light, perturbing anything you want to measure. So it was very naturally to think if muons are affecting your physical system, they are affecting our biological system. So at the end, they are crossing us. Very few collide. Really, they cross, they pass by, but they ionize whatever within some given range, whatever is passing by, strip of electrons. And then in cells, then there is a chemical competition. So imagine that you have one molecule that fills the muon, and I strip you electrons, but you are very strong. You don't want to share electrons. So you will go to the next one and say, you are weaker in electrons, so I will take your electrons and let you fight. And then the system, the chain of reactions, go to the weakest ones. And the weakest ones are the most interested in cells, because if you want to balance energy, you need something that very easily changes energy from one side to the other. So whenever you are just exchanging energy, and this is how you store energy with some molecules, is just by redox reactions with very tiny difference in energies. So therefore, at the end, something that in principle couldn't affect, and by the way, this topic started in the 60s when the muons were discovered. And people thought that DNA was affected, and it was soon showed that this was not right. Muons don't basically collide, they only ionize. So the question is, how does ionization change cellular process? They're having a few experiments in several underground labs for about 10, 20 years. One group isolated, sometimes not that well treated by physicists, but okay, they tried to do the best they could. We had another more modern view. We equip two real laboratories. One is underground, another is on surface. Basically, one equal to the other. And now we open this space, like when you go to, you told me that you are doing these big calculations. You go to a computer, you ask for hours, days, or weeks of calculations. So that means these teams, they come and say, well, I will need for my experiment 2 weeks, 3 weeks. So we provide the space, some support, etc. And they do their experiments. And it's been a big success because we brought a strong community that they are finding that there are lots of stresses that they want to understand, and this is one of the stresses. There are projects studying life in heavy water. So maybe not in the heavy water in snow, but they found that there is some organisms living. Heavy water should be highly toxic, so you shouldn't drink it. But it seems that some bacteria can live in heavy water. Viral infection, I will mention very quickly. Aging is very affected by muons. And the question is whether this is a stochastic or deterministic mechanism. And also, there is lots of panic from people trying to, that if you learn something about aging. Origin of multicellularity, so people came with ideas on, they knew from the biological side that there was stress, etc., and they understood that muons create, well, and then we showed to them that muons, the lack of muons created that stress. So let me finish with one example, just one. And one kind of dream just to you show me some images of your micron balls. This is much larger. Those are worms. They are called C. elegans. They are very much used. It's a model organism that is used, for example, for understanding how neurons behave, etc., etc. So in biochemistry, it's widely used. They are here, going over there, they have their happy life. They have a cycle of 20 days or so. What this group has studied is what happens to them now after the pandemic. There were lots of study of viruses with this virus, or say another virus. Affects their life, but the virus doesn't kill the worm. And they study what happens with this under different types of stresses. Blah, blah, blah. And at some point they came, we would like to see what happens if we make the same experiment underground. And they did. And the maybe surprising thing is that it's by far the largest stress that the worm got. I insist, it's the same experiment, you just place it underground. Same light conditions, same temperature conditions, etc., etc. Yeah. Principle, the only difference that we can account for is lack of muons. They are now studying in detail because the good thing is they can study all the molecules involved, all the genes that are expressed, etc. So just to finish, this is what will happen if we go to Mars. If we humans or life wants to go to Mars, we will go through a place that will not have muons. So what we are demonstrating with this experiment and many others that will continue coming is that the lack of muons will affect. That doesn't mean that we are not going to live. Is that we are going to be stressed. DNA is not going to be repaired, etc. So in these trips, we have to test what happens. And that's why we started and we bought, this is a microgravity system made by the European Space Agency. So you put the worms here. You rotate with a given with software manipulates, etc., so that you average gravity at the level you want. Well, how would you want? At least 1% of G up to whatever gravity. And then with that, what we are trying is to get closer to reproduce what happens in a trip. I need one more thing. So for the ones that are eager to try a new field, I need an accelerator. Because then, of course, if you go to space, you will have protons hitting you. Right? There will not be muons, but there will be protons. I mean, you have to put your just kind of, maybe we can go to Elon Musk. We can ask for a ship. We put it underground. We have some accelerator. We don't need that strong accelerator. Now these new plasma accelerators may be compact because you don't need a strong new proton flux, etc. The idea is at the end, simulate what happens during a year with organisms when they are in conditions that are somewhat closer to a tripping space. This is something that we are in the first phases, but we will try to do it. Please come to Canfranc and visit us. It's a nice place to visit. Thank you.
Thank you, Carlos. We have time for questions for the program. Biology.
Exactly. This is yeah.
I'm actually curious about, I think it was a paper you wrote about the Bayesian invariance of the neutrino hierarchy. So I think I might have read or misread, but are you only using Jeffreys priors for?
Yeah. Well, we tried several things because this paper, in fact, is we already wrote two, and not, but at some point will come a third one, because at some point we will say something like it's not anymore strong. It's like that. So I mean, by Bayesian, it's very controversial because some people. Well, there is an anti-Bayesian community, first of all, and then of course then there are some people that tell you, well, and just make not posterior. The word doesn't come to me. How you distribute your parameters, which is your initial prior. Sorry, the word didn't come. So that means you can find a prior here. Imagine I have a prior that makes this 100 times bigger than this one. So that means, of course, so that means there will always be priors that chooses the option you want. Mm-hmm. And then we have lots of discussion with experts on this and what is here or there, etc. So at the end, we created a controversy. I think most people will be willing to keep pushing on understanding this better. And at some point, if you move this a little bit down, then many people will say there is no space for that. So there are technical issues, and then there have been lots of discussions whether there are objective priors or which type of priors you use. But the summary is, to me, is the theory. In theory, there's always a prior. And this is what I'm putting in theory. Is that if I have the idea of having the same mechanism means that I cannot have this forever. So mass cannot be 10 to minus 18. Because if mass can be 10 to minus 18, this division, this is ridiculous. It will never wait. So it will wait all the other subparameters. So that's why this is very important. If you think that this is right, then the conclusion is unavoidable. So I mean, it's more important the physics, if you want, that you want to put in the input. So you think that this is right or not? If you think that this may not be right, forget this. It's academic if you want to get access.
But isn't there like already data on these types, like with nova and
yes, you're right. I didn't say anything about that because it's not conclusive. But yeah, you're right. There are seven
priors, I guess.
No. This is frequentist. So they take data, they compare what happens to neutrino oscillations for neutrinos, oscillations for antineutrinos, and then from there they can see differences. And yeah, there is an indication of favorable, normal versus inverted, but it's not conclusive.
Question about the axon experiment.
Yeah.
When are you starting to take data?
Yeah, okay. I wrote it, but it's weird. So that means why I influence, I would say, on going in this direction is that this space, the dark color is the only thing that has been done. All this is work in progress. Mad Max is at the level of generating the signal is probably the best option. They have some dielectric mirrors. It's a great idea. They will generate, if this happens, more signal. But this is so wide because they claim that at some point they will have some way to detect it. So nobody knows how to amplify here because so of course you can amplify signal at above 50 gigahertz. It has been done a lot, but not at low temperatures. So your temperature will be 30, so that means you will have a level of noise that you cannot reduce. So you have to go to superconducting devices, and this is technology to develop. So that's why, so for us, cavities is a way to have a control signal, compact, etc. For us, the interesting is developing technology that detects with the narrower you can band, but really very low noise. So that means that you go to ultra low noise. That's the idea. So this is the space free. So, but the answer to your question is this is 2 years development, 2 years first prototype, 5 years data, 10 years. Just retaining time.
Questions?
Okay.
Not, let's thank Carlos again.